Hello and welcome back. This video will continue on with section 10.1 and I want to start out with a question which is when we're looking at R, so R is going to be the linear correlation coefficient. We know that R is somewhere between -1 and 1, and the closer R is to these endpoints, to 1 and -1, the more we know that our data is going to be either it is going to be linearly correlated. The closer R is to 0, the less linearly correlated the data will be. So the question is, how close does R have to be to 1 before we can say, yeah, the data does look linearly correlated? So in order to answer that question, how close does R have to be to 1 or to -1? Well, to answer that, we'll just use a hypothesis test. Remember that, so if R is the linear correlation coefficient for a sample, rho is the linear correlation coefficient for the population. So the null hypothesis is that the linear correlation coefficient is going to be equal to 0, meaning that our null hypothesis is that the population is not linearly correlated. Our null hypothesis is that rho is not equal to 0, as in the population is linearly correlated. So again, with our hypothesis test, if R is really close to 1, we can say that, well, it doesn't seem likely that rho would be close to 1. Sorry, it does seem likely that rho will be close to 1, so rho is not going to be 0. So by examining R, and by examining how close it is to 1 or to -1, will give us an idea of where the population should be. And then with, for instance, a bigger sample size, we can say more confidently that rho should be closer to R. If we only have a very small sample size, well, rho and R might not be very, very close because our sample might not be typical of the population. Let's apply this. This will work almost exactly like all of our hypothesis tests from before. We have a test statistic. This is the same as the student t-distribution that we use for means when we are looking at normal populations. So the student t-distribution we also use to estimate mu, the mean of a population. So we'll also use this to test linear correlation. And this formula is a little bit messy. R divided by the square root of 1 minus r squared over n minus 2. Again, we will let the computer do this for us. And then from the test statistic, we will calculate the p-value. If the p-value is too big, we can't say anything, we can't reject it. If the p-value is less than the significance level, we reject the null hypothesis. One thing I quickly want to mention, though, normally with hypothesis tests for correlation, our null hypothesis is going to be rho is equal to 0, as in the population is not linearly correlated. And the alternative hypothesis is going to be that rho is not equal to 0, as in it's going to be closer to 1 or -1, meaning that it is linearly correlated. Sometimes, not necessarily often in this class, we might want to test if rho is bigger than 0 or less than 0 explicitly. When rho is bigger than 0, that means that we're positively correlated, so it's both linear and pointing up. When rho is less than 0, it should be linear and pointing down. So we can do hypothesis tests for this, but we are just going to focus on this situation up here, testing if there is linear correlation, not if there is positive or negative linear correlation. Let's go through an example. So we'll use the following data, which is in StatCrunch, which I'll flip to in a second, to test the claim that there is linear correlation between shoe size and height. And we'll test it with a 0.05 significance level. So let's write down, just like we have been, what we'll just go through all the hypothesis test steps. So our initial claim is that shoe size and height are linearly correlated. Okay. And symbolically, what this means is that our linear correlation coefficient for the entire population of all peoples with heights and shoe sizes is that the linear correlation coefficient should not be 0. If it were 0, there would be no linear correlation. We're going to claim that it's definitely not 0. So the null and alternative hypotheses, just like we saw before, the null hypothesis should be that the linear correlation coefficient should be equal to 0. The null hypothesis is always an equal sign. And the alternative hypothesis is that it is not equal to 0. The significance level, which was stated up above, was 0.05. And now we need to compute our test statistic. So in order to compute the test statistic, we need to know R and N and plug all this into the computer. Luckily, the computer will do all of this for us. So let's load up StatCrunch. And here we have all of our data. We have 19 data points, and we have the paired data between shoe size and height. And shoe size here is listed actually in length, so this is just the length of the shoe, I think, in centimeters. So we want to see if there is a linear correlation between these two. So one thing that we can do is we can come to statistics, come to summary stats, and see if there is see what the linear correlation would be. And we need to select both the shoe length and the height. And there's no other options we need to select here, so we can just compute. So the linear correlation is going to be about 0.54. Okay, so that's not super close to 1 or -1. It's fairly close. It's right in between. Excuse me. It's pretty much right in between 0 and 1. So the question is it close enough to 1, or is it close enough to 0 to say that there's no linear correlation? So what we'll do is we have to do the hypothesis test, and to do this, we come to statistic down to regression. Regression is what we'll talk about in the next section, which is in fact drawing the line for linear correlation. So that's all that means for the moment. And we are looking at linear correlation, so we get to click on this first one, simple linear, and it'll bring up this. Our x variable is going to be the shoe length. Our y variable is going to be height. And we are going to perform a hypothesis test. For the moment, we're going to ignore the h0 being the intercept being 0 and the intercept being not 0. What we're going to look at is the slope being 0 and slope not being 0. This is what corresponds to our linear correlation coefficient. So for the moment, we just want the slope to be equal to 0 and not equal to 0. This is our null and alternative hypothesis in the language of StatCrunch. We will then compute, and we have a rather large table with lots of information. And we'll just go through some of this. So we have our two variables, which we call the dependent independent variable, being the height and the shoe print length. sample size, for instance, is 9. And here we have R, our linear correlation coefficient. And it is the same number that we had before, about 0.54. So that's the nice bit of information there. And there's R. And what we'll do is we'll come down to the second line where it says slope. This is going to correspond to our null and alternative hypothesis. Just remember that it's slope. And if we come across, here is our our test statistic. So if we round it to let's say 3 places, we have 2.642. So coming back here, our test statistic T is 2.642. And the p-value, which is right next to it, is 0.017. Let's round it to three places as well. 0.017. So our test statistic and our p-value is going to correspond to our slope. And just to give you an idea of what why we want to look at the slope of the line is how fast it goes up and down. It's going to be the rise over the run, the angle at which it's pointing upward. So when we're looking at determining if something is a line, what we're worried about is the slope. So this is kind of why we want to be worried about this line here. But in any case, we can find the test statistic, we can find the p-value, and we can compare our p-value to our significance level. And since the p-value, which is equal to 0.017, is less than alpha, we reject. So what did H0 represent? H0 represented our linear coefficient being 0, meaning that there is no linear correlation. We reject that. So we get to conclude that there is sufficient evidence that height and shoe size are linearly correlated. And this is because we got to reject the null hypothesis, which said that they aren't linearly correlated. So one important thing to remember in all this is that correlation does not imply causation. So from this, we can't conclude that your shoe size makes you taller, or the fact that you're tall makes your shoe size bigger. It could be that both of these are caused by the same thing, or they're completely unrelated. In this case, they are probably related, and it's probably something else will cause both of those. My favorite thing is the fact that as the number of pirates go down, global warming will increase. But pirates don't cause global warming doesn't cause a lack of pirates. So this is just something silly to remember, that just because things are correlated doesn't mean that they're causally, doesn't mean that there is causation between them.